Okay, now we're going to do the examples as well as some of the homework exercise of chapter 15. The first example, what changes need to be made to change the two-pole low-pass design to a four-pole design? All you had to do, you add the identical section except for the gain setting resistors, and then you choose R1 to R4 based on the table for the four-pole design. And there you find the filter. Important factor here is the resistor ratio of the first section need to be 0.152. The gain is for the gain of 1.152. The second section need to be 1.235 for the gain of 2.235. Always use standard values if possible. The low-pass filter can be changed to a high-pass filter by simply reversing the resistor values, this resistance here, with a capacitor in the selective circuit. For four-pole design, the gain setting resistors is unchanged. There's the low-pass filter. I want you to see here, there's the capacitor, there's a capacitor. For the high-pass filter, the positions of the capacitor and the resistor changes. Here you can see now, in the low-pass, this was a capacitor. In a high-pass, this one is a resistor. Modify the four-pole low-pass Butterworth design for a bezel response. Divide the resistors by the correction factors on the bezel table and change the gain setting resistor to the ratio of a table. There can you see the bezel low-pass filter. Example 15.1, a certain band-pass filter has a center frequency of 15 kHz, a bandwidth of 1 kHz. I want you to determine the Q and classify the filter as a narrow or a wide band. In this particular case, Q is equal to F0 divided by bandwidth. That's 15 kHz divided by 1 kHz is equal to 15. Because your Q is bigger than 10, this is regarded as a narrow band filter. Example 15.2, if resistor R2 in the feedback circuit of an active single pole filter of the type in figure 15.6 is 10K, what value must R1 be to obtain a maximally flat Butterworth response? Make use of formula R1, R2 is 0.586. You manipulate for R1, substitute the values and you get a value of 5.860. And you're using the nearest available value, standard 5% value of 5.6 kilo will get you very close to the ideal Butterworth response. Example 15.3, determine the critical frequency of a Salicki low-pass filter in figure 15.11 and set the value of R1 for approximate Butterworth response. There you can see figure 15.11. Since RA is equal to RB is equal to R is equal to 1K, CA is equal to CB is equal to 0.022 microfarad. Use the formula S is equal to 1 divided by 2 pi RC. Substitute that value and you get an answer there of 7.23 kilohertz. For a Butterworth response, R1 divided by R2 is equal to 0.586. Substitute, manipulate for R1 and you find where R1 is equal to 0.586 multiplied by 1K is 586 ohm. And then we select the standard value as near as possible to the calculated value. 15.4. For the four-pole filter circuit in 15.12b, we're talking about this filter here. Determine the capacitance value required to produce a critical frequency of 2680 Hz if all the resistors in RC low-pass circuits are 1.8 kilo ohm. Also select values for the feedback resistor to get a Butterworth response. Both stages must have the same, assuming equal value capacitors. So therefore, calculate FC is 1 divided by 2 pi RC. Substitute the values there of a resistor as well as the frequency. And we find there that the capacitor value is equal to 0.033 microfarads. Therefore, we might say that CA1 is equal to CB1 is equal to CA2 is equal to CB2. And that is equal to 0.033 microfarad. Now also select for simplicity, refer to table 15.1 for a Butterworth response in the first stage. DF is equal to 1.848, and therefore R1 is equal to 0.152 multiplied by R2. It's 0.152 multiplied by 1.8K is 274. You choose the nearest available value, and that's 270 ohm. In the second stage, DF is 0.765 multiplied by R3 divided by R4 is equal to 1.235. Therefore, R3 is 1.235 multiplied by R4, and that is equal to 1.235 multiplied by 1.8K is 2.22K. Nearest available value in this case is 2.2 kilo ohm. Choose value for the Sally-Key high-pass filter in figure 15.15 to implement an equal value second order Butterworth response with a critical frequency of approximately 10 kilohertz. We start by selecting the value of RA and RB. R1 and R2 can also be the same values as RA and RB for simplicity. So R is equal to RA is equal to RB is equal to R2 is equal to 3.3K. So therefore, next calculate the capacitance value for FC is equal to 1 divided by 2 pi RC. So C is equal to 1 divided by 2 pi RFC. So C is calculated as 0.0048 microfarad. For Butterworth response, the damping factor must be 1.414, and R1 R2 is equal to 0.586. So the ratio R1 is equal to 0.586 multiplied by R2 is equal to 0.586 multiplied by 3.3K is equal to 1,93 kilo ohm. If you had chosen R1 to be 3.3K, then R2 is equal to R1 divided by 0.586 is equal to 5.63 kilo ohm. Either way, the approximate Butterworth response is realized by choosing the nearest standard values. Example 15.6. Determine the center frequency, the maximum gain, and bandwidth for the filter in figure 15.19. We start off, F0 is equal to 1 divided by 2 pi C multiplied by the square root of R1 plus R3 divided by R1 plus R3 plus R1 multiplied by R3 multiplied by R2. Substitute that values and you find where 736 Hertz. A0 is R2 divided by 2R1 is 180K divided by 2 times 2, 68K. That's 1.32. So Q is equal to pi multiplied by F0 multiplied by C multiplied by R2. Substitute the values and you find the value of 4.16. Bandwidth, F0 divided by Q, that's 736 Hertz divided by 4.16, and bandwidth is equal to 177 Hertz. Determine the center frequency, the Q, and the bandwidth for the pass band of a state variable filter in figure 15.22. In this case, F critical 1 divided by 2 pi R4 C1. Substitute the values and you find where 7.23 kilohertz. The center frequency is approximately equal to the critical frequency of integrators. So F0 is equal to FC is 7.23 kilohertz. So Q is equal to 1 upon 3 multiplied by R5 divided by R6 plus 1. If you substitute the values, you get 33.67 for a factor for Q. Bandwidth F0 divided by Q, 7.23 kilohertz divided by 33.7, that gives you 215 hertz. Verify that the bandstop filter in figure 15.26 has a center frequency of 60 hertz and optimize the filter for Q of 10. F0 equals to FC are the integrated states. In practice, component values are critical. F0, in other words, is 1 upon 2 pi R4 multiplied by C1. Substitute the values and you find a value of 60 hertz. You can obtain a Q of 10 by choosing R6 and then calculate R5. So from Q is equal to 1 upon 3 R5 over R6 plus 1. I manipulate for R5 is equal to 3Q minus 1 divided by R6. So I choose R6 to be 3.3K, then R5 is 3 times 10 minus 1, so the value is 95.7K. You use the nearest standard value of 100K. Basic problems. I'm going to do section 15.1 number 3. A single pole high pass filter has a frequency selective circuit with R is equal to 2.2K and C is equal to 0.0015 microfarad. What is the critical frequency? Can you determine the bandwidth from the available information? So you start with a critical frequency 1 upon 2 pi RC. That gives you a value of 48.2 Hertz. And then what is a bandwidth of a bandpass filter whose critical frequencies are 3.3 kilohertz and 3.9 kilohertz? What is the Q factor? Bandwidth FC2 minus FC1, 3.9 kilohertz minus 3.2 kilohertz. That gives you 0.7 kilohertz or 700 hertz. 50.2 number 7. What is the damping factor in each active filter shown in figure 15.43? Which filter are approximately optimized for Butterworth response? We start off with the A part, that is now this circuit here. For second order first state, DF is equal to 2 minus R3 over R4. That gives you a factor of 1. So that is not a Butterworth filter. Number B, this one here, second order, same formula, 1.44, at approximately a Butterworth filter. And then the last one, DF works out at 1.67. That's a third order two states, first state 2 poles. And that is DF is equal to 1.67. That's also not a Butterworth filter. Number 11, determine the critical frequency in figure 15.45. F critical, 1 divided by 2 pi square root of R1, R2, C1, C2. Value is 190 Hertz. The active low pass filter without changing the response curve adjusts for component values in the filter of figure 15.45. R1 is equal to R is equal to R1, R2, R5 is equal to R6, and C is equal to C1, C2 is equal to C3 and C4. So C is equal to 0.22 microfarads for both stages. Critical frequency 1 upon 2 pi frequency R squared C2 C squared. So R is equal to 3.81 kilo ohm, and choose R is equal to NAV value as 3.9 kilo ohm. A low pass filter, modify the filter in figure 15.45 to increase the roll-off rate while maintaining the approximate Butterworth response. There you can see the filter. If you change it, you exchange the position of resistors and the capacitor, see figure 15.3. Section 15.4, active high pass filter. For the filter in figure 15.46a, how to increase the critical frequency and how to increase the gain. First of all, I will decrease R1 and R2 or C1 and C2, or I will increase R3 or decrease R4. Okay.